So I feel like I don't do the planets justice. I mean, the planets are so awesome, and I kind of condense kind of quickly some of the highlights about the planets, okay? So we talked about Mercury, and now we're skipping around. We're going to talk about the red planet, Mars. Where is Mars relative to Earth?
Right next to it.
Right next to it, yes. Is it closer to the sun or farther from the sun? Farther from the sun, perfect. Mars is a very busy place. And again, I feel like I don't do it justice. There's so many awesome photographs of Mars. There's so many awesome videos of Mars, like live, like I don't know, live, but recorded videos. Mars has dust devils. It's just awesome. Mars is so cool. So my few slides aren't going to do it justice. But the other day when I brought in a video about the terrestrial planets anyway, one of the things he mentioned was the caps. Do you remember he said it's not, it has polar caps, like Earth has polar caps, but it's not solid H2O, it's solid carbon dioxide. Very good. It is solid carbon dioxide.
CO2?
CO2, yep, carbon dioxide.
Well, so all we gotta do is melt it.
Melt it and then, yeah. You terraformer people.
Just drop a couple asteroids on it and take it down real fast.
Yeah. So if we melt it, then, yeah, it'll add more CO2 to the atmosphere, and it can warm, and what's that?
The conditions would be really hellish.
Oh, my goodness. So you kind of see the caps up here, right? Now, Mars has seasons. Why does the Earth have seasons? Tilted axis of rotation, exactly. So this is trying to show you the Martian, I love the word Martian, the Martian tilted axis of rotation here. Kind of that arrow is kind of showing you. So it's directed, you know. Can you kind of see the how do I say this? The ellipse of the orbit, the Martian orbit? Yeah. And the sun's kind of off center at one foci. Exactly kind of all the planets have their orbits and shapes of ellipses, and the sun is off center at the foci, common foci. So anyway. What else do we got? Mars spins on its axis of rotation once every 24 hours. That's kind of like Earth. And so the thing about Mars, and if you have to have a very good telescope. I've never seen any like surface features on Mars. But apparently, if you have a good telescope, and I've looked for good telescopes, I can still never see any feature on Mars. You can actually kind of see some kind of dust storms on Mars, kind of as it rotates, kind of spin around. So kind of early on, we could actually kind of see this. Somebody was asking, how do we know that the planets rotate? Actually, we can kind of see those dust storms rotating around. It is so cool. Let's see. Sometimes I put this on a test. I don't know. Like I said, that sheet about your Unit 2 exam, I'm not sure. It's tentative. I will make up the test this weekend, and if there's anything different than what I gave you for your review sheet, I'll give you an amended review sheet. But it's red because of iron oxide, okay? Let's see, what's an AU? Did you guys tell me? Astronomical unit, very good. And how big is it? Yeah, distance between the Earth and the Sun. So it's located about 1.5 AUs from the Sun. Earth is 1 AU, Mars 1.5 AU. Let's see. It's significantly smaller than the Earth. So which planet is most closely in size to the Earth? Do you remember? It's not Mars.
Venus.
It is Venus. Yep. And we're going to talk about Venus coming up here in a minute. So again, it doesn't really do it justice. This is kind of a flattened out version of Mars. You can see the craters, okay? It's more heavily cratered than Earth because it doesn't have the weathering features that Earth has had over the eons. Let's see. I've got some close-up pictures, but a couple of popular Martian features. One is this Valles Marineris. I kind of think of it as spaghetti sauce, Valles Marineris. And it is near the equator region, and it's kind of like the Grand Canyon, but way longer. I think if Malays or Valles, like valley, this is like valley, Mariner Valley, Valles Marineris, okay, Mariner Valley. If it was on Earth, it would stretch, I think, across our continent, basically. What else do we have? We have volcanoes, but they're dormant. And I think, did I put a question mark on is Mars geologically active? Okay. see, northern hemisphere is a little bit lower than the southern hemisphere. And there's this kind of upward bulge called the Theris bulge. So
Olympus Mons is such a cool name.
it is, Olympus Mons is a cool name. Oh, I did have this on here. So this is the volcano, wait, nope. This is the trench, Valles Marineris, and Olympus Mons is the extinct volcano. And here's a picture, a couple pictures. This is a picture of Olympus Mons. The center part they call a caldera, and actually that term caldera can apply to like volcanoes on the earth. It's just kind of, it blew its cap, basically. Okay? And it is like, I think the size of Missouri. It is very big. And then this is that trench, this is that valley, that trench, Valles Marineris. Yeah. So again, there's so many other cooler pictures out there. But these are just a couple to show you Mars. Mars is, like I said, definitely we have a presence on Mars right now with regard to our rovers, our spacecraft in orbit. Okay. This is a surface feature on Mars to kind of highlight, this would be like where water flowed, kind of show you the kind of meandering of flowing water, leaving a path there. So this slide says, is there water flowing on Mars now? No, not routinely. I will say that there's been some excitement, activity maybe caught by some of the rovers that are there, about maybe structures that look like this and then later on they look like something else. So that water is actually maybe subliming or flowing a little bit, I don't know. But in order to have liquid water, it's kind of a chemistry thing. In order to have liquid water, you have to have those little water molecules that maybe want to stick together to be liquid. They can't be too cold or they'll be ice. Okay, they can't be too warm or they'll be gas. And actually you can monkey with the pressure to kind of get something to solidify or vaporize too. So it's a pressure and a temperature thing. And right now Mars doesn't really generally have the pressures and temperatures that will work for liquid water. This is again the surface of Mars, nice and cratered. Okay, again, like this slide emphasizes, we don't see, we see a lot of craters because we haven't had the erosion, the wind erosion, the water erosion. We do see some kind of, how do I say, subtle erosion around the craters that suggests that liquid water once flowed, similar to kind of the little meandering thing you saw a little minute ago. Liquid water used to flow. I have a slide coming up, you're like, well, why doesn't it flow now? Well, I already told you pressures and temperatures. Well, why did the pressure and temperature change? Let's see. B says a computer-generated perspective, and then C is back to actually looking at the surface of Mars in the infrared region, trying to get kind of some thermal information. But definitely with C, you can kind of see, I think they call them tributaries, like the body of water and kind of it's kind of filling out liquid water. So side by side, if I were to ask me, I might say these are like from the same planet. They are not. This is from Mars, and this is from Earth. Mars, Earth, Mars, Earth. So I know, you're like, that's kind of cool. You might recognize this kind of pebbly sort of thing is basically over time we can get those pebbles on Earth by liquid water again, making nice little rocks that can kind of become embedded together as that liquid water dries.
Yeah, it looks more eroded on, it looks smoother on Mars.
Looks smoother on Mars? Yeah. So you're like, in order to understand other planets, we'd look at our own planet, and how did we get that? We got that from liquid water weathering. So you're like, there you go.
Just like how water can make glass not sharp over time.
Right, yes. Yep. And if you have like a rock tumbler, kind of, you put chemicals and you've also put liquid in there to kind of smooth off the edges. Exactly. This, I kind of told you, this actually as a current phenomenon that's been captured. And those dark streaks are actually, I think I'm thinking of this right, where they've seen some kind of movement with regard to, not like alien movement, but they've seen some movement that looks like that water is actually kind of at least changing its form, maybe from its solid to maybe subliming, solid straight to a gas. So this slide says why. Why is Mars so dry now? You know, it's got the caps, but it's solid CO2, not solid H2O. In order to make sense of this, I like this figure down here, because here we have early Mars, and then on the right we have Mars today. So when I go, what is that? Solar wind, yep. So the yellow things are the solar wind here, okay? So the solar wind was blowing before, and the solar wind is blowing now. In order to kind of make sense of this, though, let's see. I know, okay, we're playing charades. So this is the Earth, okay? And what is this? Nope, it's not. It's beyond the mantle. It's this big thing. Not the ozone. R starts with letter M. Magnetosphere. Thank you, Lindsay. Yep. Yeah, magnetosphere, exactly. And planets like Earth and Mars can have a magnetosphere if they're sloshing around with regard to their core, if they have liquid in their core. Now, the other day, I took a piece of pizza from my, oh, we're gonna get hungry here. I took a full pizza, took one slice here, and what did you tell me about that slice with regard to its temperature? It's gonna cool faster. Yeah, you told me that one slice of pizza is gonna cool down a lot faster than my whole big pizza, and you're totally right. Okay. So the thing about Mars is it cooled down more quickly than the Earth. Okay, so Mars is that little piece of pizza. And as it cooled down, basically, even though it's spinning on its axis, it rotates once every 24 hours, kind of like Earth, that it's solidified in its core, and if it's not liquid, it can't go ahead and create one of these.
So it's got no.
Yes, and Ty's saying, so it has no magnetic field, magnetosphere, same thing, magnetic field, magnetosphere. No, it has a very slim one. The magnetic field here, can you see the purple? Or, I don't know what color, yeah, it's kind of purple. Okay, that's the magnetic field it used to have. So you're like, well, what does that do? Well, the magnetic field on Earth actually protects us from the sun's charged particles. Okay, so if Earth didn't have a magnetic field, we'd have more solar wind we'd be at the mercy more of the solar wind, the charged particles from the sun. And so that's what Mars became, more, it lost its protective, okay.
So once the magnetic field went, like its atmosphere went, then I guess maybe.
Yes, the thing about when its magnetic field went, it was more, like I said, kind of open to the solar wind, basically stripping away its atmosphere downwind.
Oh man, so we can't just melt the.
Right.
It would just go off.
Yeah, so that's what Ty's saying. So if we did melt the CO2 at the poles to try to put gaseous CO2 in the atmosphere, the solar wind is going to have an issue with regard to blowing it away because it doesn't have a magnetosphere. Yeah, problematic.
So we need to get that magnetosphere.
Yeah,
activated.
how do we
Yes, we
get
need
the
to kickstart the magnetosphere. Keep thinking.
Better use for the 6,000 nuclear weapons.
Oh, maybe. I don't know. So what this talks about is the greenhouse effect. So let's see, we talked about the greenhouse effect. What's an example of greenhouse gases on Earth? Cows. Methane, very good. Methane, CO2 gas. How about another one? Refineries, CO2 from refineries, and water vapor. Yeah, those are all greenhouse gases. Very good. Okay, and so with being more susceptible to the solar wind, it lost its atmosphere, so it lost its blanket. That's what I call the CO2 or the greenhouse gases. So it's a lot cooler than it used to be. So it used to be warmer.
So we need to just take a bunch of blankets to it.
You take a bunch of blankets. Make Mars warm again. Very good. Okay, So you guys told me Venus is much more in size to the Earth than Mars is, and you're right. Mars is smaller than the Earth. Venus is similar in size. So kind of up there in the upper corner, I went ahead and brought in Earth and Venus. Of course, the gray thing at the upper corner is the core. What is the orange part beyond the core? The mantle. Very good. So I'm talking about these guys up here. We have the core, the mantle. What's at the very top? There's letter C.
Yeah, crust.
Crust. The very top is crust, yep. And then what's the crust and the top starts with letter L, the top part of the mantle? Lithosphere. Yeah, very good. So that's kind of what we have going on. Now, I think I said we think Venus is probably got some liquid in the, and I call it liquid, but really it's kind of a slow-moving solid. It's like plastic. It's geologically active in part because of its size. It's kind of like, it's not one piece of pizza. It's maybe like 4 pieces of pizza cooling down. Okay?
What's its
So-
magnetic field look like?
And it doesn't have much of a magnetic field, which seems weird because it's ooey gooey. What we're going to see about, I think I got this right, Venus, it rotates on its axis very slowly. It's upside down and very slowly. So if it's not rotating, it can't spin that and create the magnetosphere.
So it's not as, it's stronger than Mars's though? Probably.
I think so. He's asking about the magnetic field, is it stronger than Mars? And I'd have to double check. So,
'Cause, I mean, if it didn't have a magnetosphere,
terraform.
well, I mean, that is, I don't know, there's something we don't
Yeah.
understand.
Yeah. The thing about, and this may be what you're saying, I'm not sure, it does have an atmosphere, as a very thick atmosphere, and it's loaded with carbon dioxide. Let's see, what else do I have in here? Blah, 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 blah. So Venus, has anybody seen Venus lately in the nighttime sky? Oh my gosh, it is so cool. It's very bright. Okay, it's very reflective. So when we look at Venus in the nighttime sky, we're not seeing the planet itself. We're seeing the clouds around it. So, well, it's kind of a planet, but okay. So this says, how do we see through the clouds? Well, we use radar. Basically, we've had, I can't remember, it might have been Magellan. Spacecraft orbit Venus and basically map it by sending down a signal and looking for the reflected signal and going ahead and getting it fixed on the topography. So we've mapped the planet without really seeing the planet firsthand.
We went and Google mapped it.
What's that?
We went and Google mapped it pretty much.
Google mapped it. There's a Google map of Mars though.
Oh, wow.
So I don't know if there was one for Venus or not, but and this is one of the few surface photos, as far as I know, of Venus. And I think that video we watched the other day, where I think it was Professor put it together, he actually included this. This is actually the foot of the lander, and this wasn't us. This was the Soviet Union. Okay, back in the 70s, I think it was. So.
Thank you, the Soviets.
Thank you, Soviets, yes. And this is what I couldn't remember how slowly it rotates. It takes, instead of 24 hours like Earth and Mars, it takes 243 days to complete one rotation on its axis. You're like, are you serious? Mercury's really slow too, though, isn't it? Yeah. It's like, is it 180 days or something? It's,
Wow,
Mercury's really
so
slow.
one side of the planet's getting a lot of sun for a long time.
Yeah, for both Mercury and Venus, yeah. Yeah. But the difference between Venus and Mercury is does Mercury have an atmosphere? No. Venus has got a thick atmosphere. And so, actually, if that's the sun, and this is the daytime side of Venus, the nighttime side of Venus is basically the same temperature, very hot. It's got a thick atmosphere, and the atmosphere is made up of greenhouse gases. It's just chock full of CO2. So it's got a crazy thermal blanket.
Yeah, that's why I heat up so much.
Yeah. Crazy. And I think I mentioned this about the geologically active. There's no like volcanoes erupting or that sort of thing. It is I think it was on the previous slide, it's outgassing. How do I say this? It's burping. The CO2 that makes up its atmosphere is actually has come from the middle of the planet. So
That makes sense, because where
So
else
what
would it?
makes it
Yeah.
stay?
gravity, what makes it stay? That's a good point. Gravity. Yep.
And the solar wind's not powerful enough to blow it.
Yeah. Yep. Gravity. The solar wind is not blowing it downstream, as far as we can tell. And you know, Mars being smaller in size, you know, it has less gravity, so it can't. It had a harder time fighting the solar wind that blew it off, the atmosphere off. So what I started to say is they think that actually the whole surface, the whole crust of the planet melts every 750 million years. And it basically starts over again. Is that weird? I think that is weird.
It is. What does that mean? That the mantle's on the outside for a little bit until they get
Yes.
done again?
That's what I pictured. The mantle, there's no crust for a while. Yeah. Let's see. Is this on the next slide? Yeah. So I think I said 750,000 years, but it's really 750 million years. And this actually kind of talks about how this is the top thing says where did all that CO2 come from, and it came from the burping planet. Okay, Earth actually is burping too. So those greenhouse gases, the CO2, not the methane like from cows, but the CO2 greenhouse gas that's in the Earth's atmosphere, actually some of it is coming from the Earth burping. A lot of times when the Earth burps, we call that volcanic activity, or maybe a fissure or something, okay? But this says 100 million years. So let's see, 750 million years, 100 million years. So this says about, to me, that Venus has been building up its atmosphere for about 700 million years. Sorry, 100 million years. So if it restarted then 100 million years ago, it's got 650 million years left before it restarts. Does that make sense?
Do they know if it's like increasing or decreasing in greenhouse gases generally?
I don't know if I've read that. As far as I know, it's relatively constant. But if it's outgassing, you would imagine it's increasing. So, it's interesting. Venus has got problematic because if you step on Venus, well, if you step on Earth, we have all grown up with about 1 atmosphere of pressure. That kind of has influenced what we look like as a species. That's our pressure, okay? I know it feels like we don't have any pressure, but we do. We have about 13 pounds per square inch, okay? That's us on Earth. It's kind of neat if you look at what another organism would look like if it grew up on a different planet. Okay, these guys would look like bugs or something, I think, because they couldn't make tall because of the pressure.
How much pressure, if you're like staying on Venus, would you have on you?
This says 90 times this. So if you're kind of familiar with, like, if you go down and if you're a deep sea diver, you're more and more pressure,
Yeah.
that sort of thing.
Yeah.
Yeah. So 90 times the pressure you have is what you would feel like if you were on Venus.
Wow.
I know.
And that's just because of the extra atmosphere?
Yeah, that's because of the CO2 gas particles that is so thick there.
This is so
Banging.
wow.
Mm-hmm. And the gravity a little bit, but yeah. Let's see, what else do we have? Oh, so carbon dioxide, Venus has a lot of it, and here in a minute I'm going to actually, oh, Foot Bear, there's a special there. Here in a minute that I'm going to kind of compare Venus with Earth, okay? But Venus, if it didn't have the greenhouse gases it has, and I think we talked about this before, instead of the hot temperature it'd be negative 40 degrees Fahrenheit instead of 880 degrees Fahrenheit. So those greenhouse gases, yay for greenhouse gases. So there on the right, I have kind of 3 figures kind of piled on top of each other. The first figure says, basically, let's go ahead and take the Earth and we're going to move it into Venus's orbit. I don't know what we're going to do with Venus. Maybe we're going to share the orbit for a minute. Okay? So we're going to move the Earth closer to the sun. Then this says actually that would raise our surface temperatures about 30 degrees Celsius. That's a bad thing.
What? Just by going into Venus's orbit?
Mm-hmm. That's what this figure's saying. Yep.
Yeah.
So 30 degrees Celsius. Now with all of that extra heat, of course, we are a water world, right? Where our oceans are wonderful. Our oceans cover like, what is it, 2/3 or 3/4 of the earth. So all that liquid, or a large part of that liquid, actually is going to go convert from liquid to vapor. So now we have more water vapor in the Earth's atmosphere. And did you catch that I said not only is CO2 a greenhouse gas, but water vapor is also a blanket, a greenhouse gas. So now what we've done is basically added on the thermal blankets. So not only do we have an issue having more solar radiation, but now we have more greenhouse gas in our atmosphere. So that's a bad thing. Never suggest we move closer to the sun. So then actually what that can do is those extra temperatures, because of our extra greenhouse gases, make the temperatures go up, and then we can actually have more water evaporate, and then we have more greenhouse gases. So it's called a runaway positive feedback, where basically that change accelerates our increase in our surface temperatures.
And I think that's just because of where it's at in the orbit around the sun and what our sun is.
Yep. And actually, I hadn't thought you've heard of the term Goldilocks zone, okay? And so that's kind of what we're talking about, that kind of zone where you can go ahead and exist based upon, you can have liquid water based upon your temperatures and your pressures, and things are kind of a nice sort of stable thing. Yep. All right, so don't do that. What makes Earth unique? So I have a few slides now, and talking about Earth. Well, a lot of things make Earth unique. We're the only planet that has actual life on it. And we think our life is related to our temperatures, our pressures, our access to liquid water. So if we're going to look for life on other planets or moons, we need to kind of take that into consideration. So Earth has oxygen, okay? Do you guys remember, though, when you're breathing in air, it's not oxygen that you're mostly breathing in. What are you mostly breathing in?
Nitrogen.
Nitrogen, yes, very good. So it's thought, though, that 20% oxygen that now makes up the Earth's atmosphere, it actually came from, and I heard people say, if we're going to terraform, why not start with green plants? Because green plants early on were great at basically taking extra CO2 and converting that via photosynthesis to oxygen. Okay, so what else does Earth have? Well, and we think that maybe Venus is still geologically active, and Mars might also be, based upon how they're kind of cooling down since when they were first made. But the Earth has solid, what we call plate tectonics, and plate tectonics starts with letter L, are these little slabs on the lithosphere. Very good. Kind of think of the lithosphere as broken up into slabs. And can you see these yellow marks down here? Okay, these yellow marks are kind of creepy, and they are kind of where the major plates are. Let's see if we can find, we were talking about California. You guys see the one in California? Yep. Yep, there's a major plate right there. There's Hawaii. I don't necessarily, Hawaii's not a major plate. Hawaii is kind of what they call a hot spot, or kind of a thin spot, where basically the land is moving and there's like new stuff kind of poking up, kind of a thin, I guess it'd be a hot spot instead of a thin spot, kind of poking up through the Earth's lithosphere. I think that's kind of cool.
And didn't they, like Pangea? I'm thinking about Pangea.
Yeah, Pangea is coming up here in a minute, the supercontinent. Yeah. Okay, so very good. Speaking of Pangea, so our Earth has been covered by liquid water for quite some time now. And so kind of up in the upper right-hand corner, we have our continents. You know what continent is, the land masses. Our continents used to be kind of squished together in one large continent called Pangea. And then they began to kind of separate, and they've been kind of separating ever since. And then the cool thing then is, and if you were to take 1700s, somebody looking at the land masses thought, wow, isn't that interesting? Someone looking at the land masses thought, if you could, for instance, take Africa and kind of fit it together with South America and North America, doesn't it look like kind of like a puzzle piece? Like they're just ready to, yeah. And a cool thing, let's see, yeah, okay, this is Australia, right? There's a cool thing that actually, how does this work? Yeah, and this is the Antarctic, okay? That actually, these used to be together too. It does look like it. And they have seen glacier marks basically kind of go here, stop, and kind of continue down to here. Do you know what I'm saying? So they were just clearly, what? That is so cool. So our land masses used to be together. So the land masses have broken apart over time. The word stability is a good thing if you're trying to terraform a planet, including ours. Our planet is relatively stable with regard to its current sort of pattern it's in, with regard to its surface temperatures. One of the things that kind of keeps our surface temperatures stable is this cycle that's described in 4 bullets there. It's kind of describing an overall cycle. And what a cycle means, well, for instance, there's the hydrological cycle, which is just fancy for saying the water cycle. What is the water cycle? Well, this is my oceans. Okay, the sun shines on my oceans, and what happens to the water? It evaporates, exactly. It evaporates, it can cool down, it can be basically saturate the air, it can form a cloud, and then what happens from that cloud? It precipitates, yeah. So that's the water cycle, okay? Now this is kind of another cycle involving the CO2, and actually the CO2 kind of intersects with the water cycle a little bit. Kind of key to this, I was getting ready for today's lecture, key to this is, you guys told me this is rain, right? Rain has a neat effect. If you've ever gone out after the rain, doesn't the air smell wonderful? Yeah, well, see, there's that too. Sometimes it can smell kind of muddy, okay? But aside from that, one of the things that water precipitation literally does is basically scrub the air, okay? So precipitation actually kind of pulls down dust particles. Well, that's one thing for you. If you've ever gone out before it rained and it was like really dusty dry, and you go out after it rains, is it dusty dry? No. Okay, so let's just kind of look at it that way. So in a similar way, actually, precipitation can actually kind of capture gases as it falls down. So that's kind of at the crux of what this slide is telling us. If you have an ongoing cloudy day, ongoing precipitation day, and actually sometimes our Earth has gone through patterns where it has had a lot of precipitation. Okay, what that can do actually is take it can scrub the CO2 gas and make it part of your oceans. Now this is kind of neat. For those of us who love picking up shells, okay, and I haven't done a lot of it because I haven't been on the coast a whole lot, but when you pick up a shell, you're picking up, most of that shell is made up of a lot of carbonate, okay? It actually, what that little critter did to make that shell was to take CO2 in the oceans and make it part of his or her shell. Isn't that cool? Okay, so we kind of have this precipitation removing carbon dioxide going into our oceans, okay, and then life in the oceans actually kind of taking that CO2, making it part of their shell, and kind of removing that carbon from the carbon dioxide cycle, okay. So along those lines, let's see, precipitation moves CO2 from the atmosphere to the oceans, CO2 in the oceans converted to stuff. Okay, it's no longer going to be CO2. CO2 decreases, okay? As CO2 decreases, you're taking off a blanket, okay? And you're going to, cool down? Yeah, you're going to cool down. Let's see, CO2 decreases, temperature's cool, precipitation is less, and CO2 builds up again. You buy that?
Wait, so when it
CO2
rains,
builds
the
up
CO2
again.
is less?
Yep, the CO2 is removed, and then it stops raining because it cooled down, okay? Your CO2 builds up again, it warms back up again, you go ahead and get the evaporation, you get the clouds forming, we call that condensation, you get the precipitation. So we kind of have this little ebb and flow kind of thing going on. Now I'm kind of making it it's a little simplified, but actually we have seen over time, and when I say over time, I mean over lots of time. I have some pictures coming up. It's showing you the CO2 go up, the CO2 come down. This is over like hundreds of thousands of years. CO2 go up, CO2 come down. Bless you. Bless you. And we're going to see a picture, graph, of CO2 in the Earth's atmosphere coming up. And it's gone up and down a long time before humans got here. And then what I'm going to try to kind of show you, we actually call this, or Al Gore called it the end of a hockey stick. You know, if you take a hockey stick, the end of the hockey stick kind of goes up, okay? So here's up and down and up and down. And then here we have our Industrial Revolution, where we understand it's a wonderful thing. We can take what we call fossil fuels. Okay, fossil fuels are coal and gas and oil. Those are fossil fuels. We can take those and we can burn them and get energy. And so, but when we burn them to get energy, we also emit CO2. So the CO2 concentrations have gone up. That's the hockey stick part. Okay. This actually, the third bullet up here says, not only are we with our emissions, and it could be from a power plant, emissions from a power plant, emissions from a car, emissions from a jet, all those things, normal power plants like coal generated or oil, all those things emit CO2. The other problem is we are a consumption sort of society. We consume a lot. And as one of the things that we need is wood for houses, wood for paper. Okay, so as we take down trees to satisfy what we think we need, self-included, as we take down trees, that actually is taking down something that was good at removing CO2 from the atmosphere. So that's working against us too. So fossil fuels, burning fossil fuels, and deforestation kind of work in the same direction as putting more CO2 in the atmosphere. And I'm going to show you a graph here to kind of show you, now it's hard to get a fix on the global temperature, I grant you that. But sometimes, I'll try to put it in a positive light, I think we need to respect what scientists and mathematicians and statisticians do. They went to school to do, they kick things around, and they can actually come up with a representative temperature of the Earth. I know it seems kind of strange, okay, but they can. And temperatures on Earth have been rising. Let's see. So what this last part is simply saying is, we know we have an issue. I'll go over here. This is my CO2. We know we have an issue with regard to our burning of fossil fuels and our deforestation. Our CO2 is increasing. And if you increase CO2 artificially, what you've done is you have inserted something that actually, remember I told you CO2 went up, CO2 went down, CO2 went up, CO2 went down. I mean, we've been getting more CO2, less CO2, like for way before humans ever populated the Earth. Okay, but we have now added something to our little experiment called the Earth that has changed the CO2 in our atmosphere. Okay, so global warming. Now, how do I say this? I do want to point out there that the fact we've had kind of a warmer winter than usual, you cannot take just Keokuk, Iowa, and say, well, I know global warming is true because it's warm here. You can't do that. You have to leave that, honestly, to the scientists and the mathematicians and the statisticians that actually look at the globe as a whole and come up with one temperature. Okay. So with that said, now do you see these jigs and jags? They look similar, but I'll tell you the top one is actually the temperature and the bottom one is CO2. So in science, if we see something, like if this is CO2 and this is temperature, if we see something that kind of goes like that, CO2 and temperature, you're like, oh, well, okay, I think that the temperature must be affected by the CO2. Yeah. We do that all the time in science, right? Okay, so, and this is actually back in thousands of years ago. CO2 goes up, CO2 goes down. Temperature goes, or CO2 goes up, temperature goes up. CO2 goes down, temperature
So when was the highest CO2 ever recorded?
That's coming up. Well, maybe not. So this, it's hard to read, but this right here is my hockey the bottom of my hockey stick, which I don't play hockey, but, so, this is 1750, and I don't know what, but to me, it's looking about 300. And the units of CO2 here are parts per million, which is pretty low, parts per million. It's higher than parts per billion, okay? We're looking at 300 parts per million in 1750, and like a few months ago, maybe a year ago, we crossed the 400 parts per million. So, that's...
Like during the Cretaceous, it was around like 500 parts per million, right?
I don't know, I'd have to, not according to this. Not according to this graph I
Because
got
that's
here.
just what I Googled the other day. I was like, because I was curious.
Yeah. I don't know, you might be listening to the other side, I don't know. Not that the other side is dark, but scientists should hash this out, but they ought to be honest when they do. On both sides. So, the little thing here is actually kind of squished. If you were to take this and kind of make it shorter, it would look more angled. But this is just a famous place in the Hawaiian Islands that have been gauging CO2 concentrations since late 1950s. What else do I got? Okay. So, this is kind of fun. Now, you see 3 lines over here, right? You see the black line, which is the actual temperature change. Black line is the actual temperature change. The blue line down there, which is kind of nice, actually is what we think the temperature should have done without human influences. This is, you know, computers are great at forecasting. This is a forecast. The blue line is a forecast, okay, based upon just Mother Nature doing her thing. The black line, let's see if I have it right. The black line is actual. The red line, yeah. The red line is using a computer again, but saying, okay, Mother Nature, you do your thing. And actually the red line does the computer and it says, humans, you do your thing. Okay, based upon past what we've been known to do. So the point here is that actually humans doing their thing and the actual, okay, actually the computer model matches what the actual is. Okay. And the blue is minus human effect. So then I kind of finish off. I think I'm almost done. Almost done making me sad. But the white here is a glacier, and I don't know if you recognize the shape, but this is Greenland. Okay, so in 1979, the glacier covered Greenland that much. Greenland, if
The whole
you had
white
to,
area?
the whole white area. Okay, ice sheet. Okay. Then you see the white area in 2012.
That little
Yeah.
sliver?
The little kind of fragments of white. Okay. And then kind of each bullet says, who cares about global warming? And I kind of tell you the highlights of who cares. Well, we're going to lose our glaciers. The problem with losing our glaciers is that meltwater needs to go somewhere, and it will find its way to the large bodies of water, otherwise known as oceans. If we get too much water or more water in the oceans, actually that's going to increase our sea level. There was an episode of Gilligan's Island where he was actually afraid that their island was getting shrunk down by water, rising sea levels, but it wasn't. Anyway, so that's problematic. We might have more intense storms because of the extra energy, thermal energy in our atmosphere. This one, I think, kind of, this one down here, the migration of diseases, I mean, that's just ripe for a science fiction shows. Basically, we know that warm conditions are great for all sorts of nasty things. And as our temperatures that we're used to being at the equator kind of go north and south from the equator, then those conditions are going to be ripe for those terrible things that none of us want to see. Okay.
Wait,
So-
how much water was that
That melts?
this ice cap? That had to have been tons
A
of
little bit
water.
of water, right. A little bit of solid converted to liquid, yeah. Increase the... So I just kind of summarize on this slide. And let's see. Oh yeah, see the Goldilocks zone here, right? Here's the Earth. This would be what? Venus, and this would be Mars. Great. And then I kind of, and this figure from your textbook maybe is where I got my, are they geologically active? That's what the question mark is. Okay, this says, are they continuing to have volcanic activity? Well, the Earth does. Venus, question mark. Mars, really a question mark because of its size. It should have cooled down. Then we have Mercury and the Moon geologically dead. So, and the last one. Dun, dun, dun. Ooh, that was the last one. Okay. All right, so be ready for the gaseous planets on Monday. So we only have Monday, Wednesday to talk about the gas giant planets. That'll be on your test, and then your test on Friday. Never a dull moment.